Hello everybody and welcome to the tutorial. In today's tutorial we learn about yet another binary system which is called the excess notation. And the excess notation allows us to represent both positive as well as negative numbers. So in today's tutorial we are going to cover three elements, and these are: how does the excess notation work, and we're going to talk about the range, how to convert from decimal to excess and vice versa, and then we talk about something that I called length determination. So let's get to it. The excess notation comes with a specific length of digits, and that means we do have a 3 bits excess notation, right? 3 bits excess notation, and that will be based on 3 digits, the entire system. Or we can have 4 bits excess notation, or we can have 5 bits excess notation. So in each specific excess notation you have to fix the length of the binary codes. It has to be 3 digits, or it has to be 4 digits in the 4 bits, or it has to be 5 digits in the 5 bits excess notation. Now, to express 0 in the excess notation, that means we put to express 0 in the excess notation, what we do is we put 1 in the most significant bit and then as many zeros as necessary in the remaining bits. So for example, 0 in a 3 bits excess notation, 0, since we only have 3 bits, is expressed by 1 here, 0 here, and 0 here. In a 4 bits excess notation, 0 is expressed by putting 1 in the most significant bit and then zeros in the remaining bits. In 5 bits excess notation, in 5 bits excess notation we have 5 bits, so we put 1 here and then 4 zeros in the remaining bits, and so on and so forth. So you get the idea. Now, how can we build the entire system? Let's have a look. Let's drag this up a little bit. So 2 rules. I'm going to talk about 2 rules. In an in-bits excess notation, the system is capable of expressing numbers or range numbers or range from -2 to the power n to plus 2 to the power n, 2 to the power n minus 1 to 2 to the power n minus 1 minus 1, right? Okay, so this is the range. So in a 3 bits excess notation, that will be this 3 bits excess notation, this 3 bits excess notation, right, is capable of representing numbers ranging from -2 to the power 3 minus 1 is 2, right, to plus 2 to the power of, again, 3 minus 1, because n here is the number of bits. 3 minus 1 equals 2 minus 1. So that would be -4 to 3. This is the range here. Now, in addition to the range, there is something else that I want to bring to your attention before we build the entire 3 bits excess notation. The number of combinations that are possible in these 3 bits, okay, are 2 to the power of n. Now, do not confuse this with range, okay? This is range here. This is the range, which is this. This is the range, okay? minus 3 to 4. But the number of different combination is when you add all the numbers plus the 0 that can be represented. That is equal to 2 to the power of n, which in this case, since n is 3, that equals 8. Now, this is important because we're going to build on this piece of information. Now that we know about the range, okay, here, and we know about all the possible combinations in a 3 bits excess notation, let's build the entire system. Okay, so I know that I have 8 possible combinations, right? And we've said that the 0, remember that the 0 is equal to 1 here and then 2 zeros, right? So the way you do this is you have 8 combinations, so you will start by putting 4 ones in a row and then 4 zeros like this. 2, 3, these are the 3 digits. So 1, 4 ones in a row and then 4 zeros. Why? Remember that I have 8 combination, right? 8 combination here. So these are the 8 combination, and the first digit will be 4 ones and then 4 zeros. And then you divide by 2. So you have 2, excuse me, you have 2 ones, 2 zeros, 2 ones, 2 zeros, and then you divide by 2 again, so that's going to be alternating. So 1 0 1 0 1 0, sorry, 1 0 1 0 1 0. These are all the combinations. To put things in perspective for you, remember that we said the 0 is equal to 1 0 0. So it's right here. This is 0, correct? And then we have positive 1 when you go up, positive 2, positive 3, and we have minus 1, minus 2, minus 3, and minus 4. And that's it. This is a 3 bits. This here is a 3 bits excess notation system, right? These are all the numbers that it can represent. It's from minus 4 to plus 2, right? And there are 8 combination because they're 3 positive numbers, 4 negative numbers, plus the 1. You will notice here that every number that starts with 1 is either a 0 or it has to be a positive number, right? Negative numbers, they all have zeros in the most significant bit. So just keep this in mind. So now that I think we have covered how does it work, and we have covered the range. So this is done. This is done here. The next point will be to talk about how to convert from decimal to excess and vice versa. So we are at this point now. Now, before we go to this second point, there's another rule that I want to talk to you about, which is if we have a 3 bits, if we have a 3 bits excess notation, there is something that is called, for this excess notation, there is something, 3 bits excess notation, there is something that is called the excess. We say that the excess of this number is 2 to the power of n minus 1. Oh, what does that mean? Let me explain more. But just follow me. So the excess for this notation is 2 raised to the power of n, where n is the digit, by the way. 2 raised to, so this is the 3 bits excess notation, 1, 2, 3. N is equal to 3. So the excess would be 2 raised to the power n minus 1 would be 2 raised to the power 2 would be 4. So usually 3 bits excess notation could be written like this. 3 bits, right? Excess 4 notation. How is that useful? we will need this when we convert from decimal to excess and vice versa. So let's take another example. If I have a 4 bits, right, excess notation, can you tell me what is the excess of this system? Well, very easy. And the excess equals 2 to the power of n minus 1, where n is the number of digits. So that means 2 to the power of 4 minus 1, which is 3, that equals 8. So the excess here, so this 4 bits excess notation could be written like 4 bits excess 8 notation. Okay, again, how's that useful? Well, it's very useful in so many different ways. As an example, let's go back to our 3 bits, and we said 3 bits is excess 4. You will see that in 3 bits excess notation, it is usually, we need the excess because the range will be -4 to 3. Let's have a look. Let's look back. Look, right. 3 bits -4 except 3. Okay, so that's a useful piece of information. And the same goes here. For 4 bits, now you know that the range, without even using this equation, remember this equation? The equation for this is the equation for the range, right? Where is it? Yeah. This is the equation for the range. Even without using this equation, now you know that if you have the excess for 4 bits, it will be -8 to +7, right? So this is how it works. This is one way getting the excess is useful. But to put things in perspective for you, we are still talking about decimal to excess. So let's get to it now that you know what the excess of a specific n bit. So we can say as a rule, an n bits excess notation, right? For an n bits excess notation, the excess will equal, or e, the excess will equal 2 to the power of n minus 1, right? You need to keep this in mind because you're going to need it. So let's say that you want to convert number 3, right? Decimal 3 to excess notation, right? So here's how you do it. First, we will follow a 2-steps algorithm to convert decimal to excess notation. Let's write down this algorithm. First, add excess to the base 10 number. Okay. Number 2, converts to unsigned binary. Now, don't worry, and it's important that you know that you're converting to unsigned binary. Don't worry, I'm going to give you an example that's going to make this super easy. So the rule here to convert from decimal to excess notation is to add the excess to the base 10 number and then convert to unsigned binary notation. So let's take an example. I want to convert 3 to excess notation, right? Okay. So if we're using 3 bits, that means the excess is 2 to the power of 3 minus 1, which is 2 to the power of 2, which is 4. If we're using 3 bits, so the excess is 4. So we add 4 to the base 10 number. The base 10 number means this number here. Add excess to it, so that would be 7. So we're done with the first step. The second step is to convert this to unsigned binary. Well, that's easy. I just need to put the weights here, or the values, and put 7. This is 7, right? Because 4 plus 2 equals 6 plus 1 equals 7. So in 3 bits, excess 4, remember notation, this here represents number exactly, number 3. You want to make sure? You want to verify that? Let's go here. Let's go back here. Look. This is plus 3. 1, 1, 1. Okay. I have a feeling that we need to take another example. Let's take a minus example, right? Let's say we want minus 3. So let's follow the algorithm. Add excess to base 10. The base 10 now is minus 3. Excess is 4. So that would be that would be just number 1. Second step is to convert it to unsigned binary, which is super easy. If we go back here, 1, 2, 4, so this here is supposed to be minus 3, right? In 3 bits excess 4 notation. Well, let's verify that. Just keep in mind, 0, 0, 1 is minus 3. And indeed, 0, 0, 1 is minus 3. Okay, so I think we covered this part. Decimal to excess. We just need to do the opposite now, which is convert the excess to decimal. We are going to follow a 2-steps algorithm, which will be exactly the opposite of the previous algorithm, right? So first we need to convert the binary to decimal. And I have covered this, by the way, in previous tutorials. Please go watch them if you want to know how to do that. And then subtract excess. So, which, by the way, if you compare, you will see this algorithm here is the opposite of this algorithm. If you need to like pause the screen and read them slowly, you will see it's the exact opposite. So here you convert the binary to decimal, and then you subtract the excess. Very, very quickly, let's try to let's take minus 3, which is 001, and try to use this algorithm to let's do minus 3 and try to convert negative 3, which is 001 in excess notation. As you can see here, 001 is minus 3. Convert this to its decimal equivalent. So first, we convert this to decimal. So 1, 2, 4. Well, convert it to decimal, again using unsigned binary. Using the rules of unsigned binary. Yeah? Just like in the upper algorithm. So that means 1. Okay, subtract excess now. We said it's excess 4, so 1 minus 4, that would be minus 3. Okay? So I hope that was easy for you. You can watch it again. If you think it's a bit hard, you'll get the hang of it. So now we've covered decimal to excess and vice versa. Last thing will be length determination. And what I mean by that is I can come and tell you, okay, please convert minus 3 to excess notation. But the thing is, I do not tell you the number of bits. I do not tell you, to 3 bits excess notation, and I do not tell you the excess as well. I do not tell you it's excess 4. So how do you figure out how many digits is going to be used? Because remember we said the excess notation, it comes with a specific length of digits, right? So you will use these equations to determine the length of the excess notation for any number. And I have explained these before, so if you think it's a bit hard, I'm not going to spend a lot of time explaining them because I already did before. So here's the equation. This is the ceiling of log base 2 x plus 1 plus 1. This is for positive numbers. Positive numbers. And this equation here, the ceiling, this means the ceiling. So the ceiling of log base 2, the absolute value of x plus 1. What are these? This is for negative numbers. Negative numbers. So again, what do we use these equations for? These equations give us the number of digits for any number if you wanted to convert it to excess notation. So x here represents the number. So again, an exam question, put -3 in excess notation, and it doesn't, and the examiner or the exam doesn't give you the number of bits. You are going to use this second question here because this is for negative and this is for positive. So let's do it. So this would be the ceiling of log base 2 of 3, right? Plus 1. So what is log base 2 of 3? It is 1.5, right? So the ceiling of this 1.5, so the ceiling of 1.5 plus 1, so this would equal 2 because the ceiling of this number 1.5 is 2, so 2 plus 1, that would equal 3, meaning we need a 3 bits excess notation, at least 3 bits excess notation to express, to represent the number -3, right? As you can see here, -3 can only be represented in 3 bits excess notation. It cannot be represented in excess 2 because excess 2, well, let's see, excess 2 would be able to represent numbers up to ranging from 2 to the power of n-1. In this case, 2 to the power of 1 to plus 2 to the power of 1 minus 1, so numbers ranging from -2 to +1. This is what excess 2 is capable of representing. So at least you need a 3 bits excess notation. By this, we have reached the end of our tutorial. I'll see you guys in the next tutorial, and I hope you benefited from this one. Thank you so much for watching.